friend, welcome to this lecture. In this lecture we will continue our study of heat equation, and if you recall in previous lecture we have discussed heat equation in an infinite region and semi-infinite region, and there in case of semi-infinite region we have discussed two cases in which we applied Fourier cosine transform and Fourier sine transform to solve the problem. Now in this lecture we will discuss the finite heat equation given in a finite domain, or we can say that here we have a finite rod is given, and again we assume the same kind of condition that here the finite rod of finite length is situated along the x axis. So one end is given at x equal to 0, another end is given at x equal to L, and the material of the rod is homogeneous, and rod is very thin, so that temperature distribution is homogeneous along the rod, and we assume that whatever condition we have assumed regarding the infinite rod in case of infinite case we assume here also, and the governing equation along with the boundary condition will take the following form. So here heat conduction in finite rod case is given like this: ut equal to kuxx, where x is lying between 0 to L, t is greater than 0, and our boundary condition is this, that u0 t equal to ul t equal to 0 at t greater than 0, and ux0 is given as f of x, where x is lying between 0 to L. So here we assume that both the end are kept at 0 temperature for all time t. So here we have this rod is x equal to, this end is x equal to 0 and this is end x equal to L, and both the end point are kept at 0 temperature, and it may happen that both the ends are having some different temperature say value, and then we can always apply our linear transform and to convert our boundary condition, non-homogeneous boundary condition as homogeneous boundary condition. I hope you recall this thing uxt, I can write it uxt as vxt plus atx plus bt. So we can find out ATBT in the sense that this vxt will take homogeneous boundary condition, and of course we have to pay the price, and this homogeneous equation will convert into a non-homogeneous equation, and we will see how we can deal this kind of problem. But before that, let us first solve the problem of this heat conduction in finite rod case with homogeneous boundary condition. So first let us solve this homogeneous problem with homogeneous boundary condition with non-homogeneous initial condition. So here we can apply finite Fourier transform and finite Fourier transform, but here we are not considering this integral transform method, rather than we are applying variable and separable method, because your equation is now in separable form, and your boundary condition is also in separable form. So here let us assume that using the separation of variable form of the solution, we assume this, that uxt is given as x of x and t of t. So using this we can put it our assume form in this equation number 20, and we can write this as x double dash upon x equal to t dash upon kt, and since this is a function of x, this is a function of t, and this is equal only when we have a constant value which is separating both the equations. So we have x double dash upon x equal to lambda and equal to t dash upon kt equal to lambda. Now again this constant lambda may take positive, negative or 0 value, but we will say that we have already considered this kind of problem, x double dash minus lambda x equal to 0 and t dash minus lambda kt equal to 0, and we have already considered the different cases and the boundary condition. What is the boundary condition given here? You know that u0 t equal to ult equal to 0, so it means that x 0 t of t equal to 0 and x of L t of t equal to 0. So since tt is not ideally equal to 0, so this implies that x of 0 equal to 0 and x of L equal to 0, and we have seen that this equation along with these boundary condition will have a non-trivial solution only when this minus lambda is a positive value. So it means that here we will take that lambda must be negative. Minus lambda is taking a positive value, say mu square, it means that lambda is equal to minus mu square. So, it means that lambda is a negative value. So, it means that based on this discussion, we can say that we observe that lambda must be negative, and let us assume that lambda equal to minus alpha I square. So, when we take lambda equal to minus alpha I square, then this can be written as two set of ordinary differential equation, x double dash plus alpha I square x equal to 0 and t dash plus alpha I square kt equal to 0, and this we can solve by writing x of x equal to a cos alpha x plus b sin alpha x, where a and b we can obtain using our initial condition, that is x 0 equal to 0 and x l equal to 0. So we are applying x 0 equal to 0, we have a equal to 0. When we take x l equal to 0, this implies that b sin alpha l equal to 0, and now if you want a non-trivial solution, b has to be non-zero. So, this sin alpha l has to be 0, and this implies that your alpha must take this value n pi by l here. So, here this is valid for every n equal to 1, 2, 3 and so on. So, we can write x n x as b n sin n pi x by l for each n. So, corresponding to each n we have a solution. So, we write solution as x n x x equal to b n sin n pi x by l. So, taking the value alpha n, and we can solve the other equation, that is t dash plus alpha square kt equal to 0. So, we can write down the solution corresponding to that also, and we can write t n t equal to c n exponential of minus n square pi square upon l square kt. Now, when we have x n x t n t, then we can write down our u n t as multiplication of this, and we can write b n into c n as new constant, that is a n. So, we can write u n t as a n exponential of minus n square pi square kt upon l square into sin n pi x by l. Now, still we have one constant here a n for each n. So, to handle this we have to use initial condition, because so far we have obtained this form only using the boundary condition, we have not utilized the initial condition. So, to handle this a n we will apply initial condition. So, here we have this thing, but before that, we, since it is true for every n, so we can apply our principle of superposition to write solution as this form, that u x t equal to summation n equal to 1 to infinity a n exponential of minus n square pi square kt upon l square into sin n pi x by l. Now, use the condition that u x 0 equal to f of x, then we can write this as f of x equal to n equal to 1 to infinity a n sin n pi x by l, because this term is nothing but 1, at t equal to 0 this is 1. So, we can write f x equal to n equal to 1 to infinity a n sin n pi x by l, x is lying between 0 to l, and this kind of thing we have already seen several times. So, we can find out our a n by using orthogonality of sin n pi x by l, and we can write a n as 2 by l 0 to l f x sin n pi x by l dx. So, it means that your a n is given in terms of initial condition, that is f of x. So, our solution is given as u x t equal to n equal to 1 to infinity a n exponential of minus n square pi square kt upon l square sin n pi x by l, where a n is given by this formula, that is 2 by l 0 to l f x sin n pi x by l dx. So, this solution is given in terms of 23. Now, so far we have not discussed anything about convergence, uniform convergence, anything we have not considered. So, we will consider this solution given in 23 is a formal series solution, and we can prove, in fact we are not proving, but we can prove that the function u x t given in 23 represent the solution of the equation if f x is twice continuously differentiable and f triple dash is piecewise continuous. So, this I am not giving. So, I can simply say that 23 is given as a formal Fourier series solution. Now, here we have we found the solution in finite rod case using variable and separable, but as I pointed out that you can find out the same by applying finite Fourier transform also. So, here to make sure that whatever method you apply you have a unique solution, we will consider the following result, which says that the solution u x t of the differential equation u t equal to u t minus k u x x equal to f of x t, x is lying between 0 to l, t is greater than 0, satisfying the initial condition that u x 0 equal to f of x and the boundary condition that u 0 t equal to f 1 t and u l t equal to f 2 t at t greater than 0. As I pointed out, you need not to consider all the time boundary conditions are 0, you need not to consider that both the end point are put at constant temperature. You can take F1 t and F2 t, and we will see that the solution of this problem, if it exists, must be unique. Okay. So, whether I should apply integral transform method or apply the variable separable method, we have a unique solution. So, let us prove this, and to prove this again we use a generalized energy function. So, here we let us say that u1 and u2 be two solution of the given problem, and let us consider the difference of this u1 minus u2. So, we satisfy the following equation: Vt equal to k V x x, where x is lying between 0 to L, t greater than 0, V0 t equal to VL t equal to 0, Vx0 equal to 0. So, here we have a homogeneous equation, homogeneous boundary condition and homogeneous initial condition, and we want to show that V is ideally equal to 0. And to show this, let us assume a generalized energy function E t as 1 upon 2 k 0 to L V square x t dt. Now, this integrand is positive, your this is positive. So, we can say that this E t is greater than 0 for all t greater than 0. So, here let us differentiate this with respect to t. We have dE by dt equal to 1 upon k V V t dx. Now, here V t I can replace by k V x x. So, we can by replacing V t by k V x x, we can write this as 0 to L V V x dx. Now, here we can use integration by part, and we can write V V x 0 to L minus 0 to L V x square dx. Now, here if you look at the bounded term, here we already know that V 0 t and V L t are given as 0. So, it means that this boundary term will simply vanish. So, it means that dE by dt equal to minus of 0 to L Vx square dx. Now, again we can say that this is something which is non-negative, but there is a minus sign here. So, dE by dt is less than or equal to 0. So, it means that E is a decreasing function of time t, and the condition Vx0 equal to 0 implies that E0 is equal to 0. If you look at here we already know that this V x0 is equal to 0. So, E of 0 is your say 0. So, E of 0 is 0, and E is a decreasing function of time function of t. It means that Et is less than or equal to 0 for all time t greater than 0. But we already know that Et is non-negative. So, Et is non-negative means here by definition your Et which we have defined here, Et is greater than or equal to 0, and what we have achieved that Et is less than or equal to 0. These two things happen together only when Et is equal to 0. So, it means that your Et is ideally equal to 0. Now, but what it means that Et is ideally equal to 0 for all t greater than 0 means that the integrand, that is V square x of t, must be ideally equal to 0. Now, what it means your V is ideally equal to 0. It means that u1 is equal to u2 for all time t. So, this shows that uniqueness of the solution. So, it means that solution of the finite solution of the heat equation in finite domain, if it exists, must be unique. Now, let us as I pointed out that if we take a non-homogeneous boundary condition, and if we do a suitable change of say in equation to make our boundary condition as homogeneous boundary condition, then we will get a homogeneous boundary condition, but we may get a non-homogeneous equation. I think let me look at here. Here we have this ut equal to k u x x, right, and u x0 equal to f of x is given, no problem. U0 t is given as f1 t, and ULT is given as f2 t, right. So, here I really do not want because we know we have solved this problem by taking f1 and f2 are 0, but we do not want to solve this. So, let us assume that Vxt is equal to uxt plus atx plus bt here. So, now we want that x equal to 0, so at x equal to 0 this must be 0, and but u0 t is f1 t. So, f1 t equal to f1 t plus this part is 0 plus bt. So, we can find out bt as minus f1 t, and at x equal to L we have this is 0 equal to f2t plus ATL minus f1t. So, we can find out our AT as f1t minus f2t divided by L. So, you can find out AT/BT, but this V xx will be same as uxx, that you can see that because this is your linear in terms of x, but Vt will be what? Vt will be ut plus a dash t x plus b dash t. So, we can write our equation as Vt minus a dash t x minus b dash t equal to k times, in place of uxx I can write vxx. So, it is vxx. So, we can write Vt equal to k vxx plus a dash t x plus b dash t. Your initial condition is what? Use v0 t is equal to 0 equal to vlt. Now, we can find out ux0. What is ux0? Your vx0 is basically vx0 will be f of x plus a0 x plus b0, which we can write it f tilde x. So, here we have this condition vx0 equal to f tilde x. So, it means that our problem is now reduced to a non-homogeneous problem by writing this as ftx, but initial condition and boundary conditions are homogeneous and initial condition is same thing. So, it means that this problem, when boundary conditions are non-homogeneous, it can be reduced to this following thing, that ut minus alpha uxx equal to fxt, x is lying between 0 to L and t is greater than 0, and boundary condition is now homogeneous and initial condition is given. So, it means that if I can solve this, then we can solve the homogeneous equation with a non-homogeneous boundary condition. In fact, whenever we have a non-homogeneous boundary condition, we have to handle in a previous case which we have written here, and by doing this we can make our boundary condition homogeneous, but there is some additional term is present in a equation which is given in this form. So, now let us solve this problem. So, consider the associated homogeneous equation ut minus alpha uxx equal to 0 when x is lying between 0 to L and t is greater than 0 here. And since the boundary conditions are homogeneous, so we can consider uxt as xxtt, and we can get our t dash upon alpha t equal to x double dash upon x equal to minus alpha lambda square, that we have just pointed out. And looking at the boundary condition x equal to 0 equal to x of L equal to 0, we say that x and x is equal to sin lambda n x, and lambda n is given as n pi by L whole square, n is greater than or equal to 0, and we can say that we can find out our solution x and x like this. And using getting idea from the homogeneous part, now we can write down that for the non-homogeneous equation, consider a solution of the form uxt equal to n equal to 1 to infinity t n t x n x, where x n x is given by this sin lambda n x, while lambda n is given by n pi by L here. So, we need to find out t and t, so that this uxt will satisfy the non-homogeneous equation number 32, that is ut minus alpha uxx equal to f of x t. So, here from the orthogonality we can find out the expression for TMT, that TMT is equal to 2 by L 0 to L uxt xmx dx. So, here if we write our uxt as n equal to 1 to infinity TNT x n x, and since we already know that x n x is sin lambda n x, then we can find out the expression for TNT by using orthogonality of x n x, and we can write down TMT as 2 by L 0 to L uxt xmx dx. In particular, for t equal to 0 I can write Tm0 equal to 2 by L 0 to L. Now, uxt at t equal to 0 is given by f of x. So, Tm0 is given as 2 by L 0 to L f of x sin m pi by m pi x by L dx equal to. So, it means that we need to solve our expression for t and t, so that this uxt will be a solution of non-homogeneous problem with the initial condition, that is Tm0 equal to 2 by L 0 to L fx sin m pi x by L dx. So, now by putting your expression this expression number 37 into our equation, and we can write our equation n equal to 1 to infinity t n dash x n minus alpha from n equal to 1 to infinity t n x n double dash equal to f x t. So, this is what our equation is ut equal to alpha uxx. Now uxt is what? Uxt is summation t and t x and x. So when you differentiate this, ut will be giving as t n dash xn, and now here if you find out uxx, so sin n pi x by l, if you differentiate it is cos n pi x by l into n pi by l, and again if you differentiate then we have a minus sign present. So we have minus alpha n equal to 1 to infinity t n x n double dash equal to this. When you simplify this, then this is the term which will create a problem. So we will write fxt as a convergent series form of in terms of x and x. So we can write fxt as n equal to 1 to infinity q n t x and x. Now what is q n t? We can find out q n t as 2 by l 0 to l fxt sin n pi x by l dx. So using the equation number 39, 40, we can write down our equation like this: n equal to 1 to infinity x n into t n dash plus lambda n square alpha t n minus q n equal to 0. Q n is given by this, x n is sin n pi x by l. Now this is 0 only when the this term is going to be 0. So it means that we have t n dash t plus lambda n square alpha t n t equal to q n t. Now this is a simple ordinary differential equation, homogeneous ordinary differential equation, and we can find out the solution using whatever method. In fact, variation of parameter method you can apply, or you can simply solve, and this problem can be written as t n t equal to t n 0 exponential of minus lambda n square alpha t plus 0 t exponential of lambda n square alpha tau minus t q n tau d tau. So once we have t n t and x n we have already obtained as sin n pi x by l, our solution uxt is given as t n t into x n x. So t n t expression we have written here. Now we already know the expression for t n 0, that is 2 by l 0 to l f xi x n xi d xi. So using the expression for t n 0, we can write uxt as n equal to 1 to infinity, this is t n 0 into exponential of minus lambda n square alpha t plus here 2 by l 0 to l exponential of lambda n square alpha t minus tau. We are just writing the expression for q and tau here, that is 2 by l 0 to l f xi tau x n xi d xi. So here we write simply the expression for q and tau. So writing the expression for q and tau and t n 0, we can write down the solution uxt as given in equation number 44. And here I am assuming that this series solution is uniformly convergent, so that we can interchange the integral sign and summation sign, and say by changing the order of integration and summation we can get the following form, that is uxt equal to 0 to l n equal to 1 to xi exponential of minus lambda n square alpha t x n x x n xi upon l by 2 f xi d xi plus 0 to l n equal to 1 to infinity this expression f xi tau x n xi d xi d tau, and which can be simplified by introducing a new function g xi t, and we can write uxt as 0 to l g xi t f xi d xi plus 0 to l g x xi t minus tau f xi tau x n xi d xi d tau, where this g x xi tau is given by this expression, that is exponential of minus lambda n square alpha t x n x x n xi divided by l by 2 summation n equal to 1 to infinity, and we call this function as green function. So it means that the solution of non-homogeneous finite domain problem can be written as this uxt equal to this, and with the help of green function which is defined like this. Is it okay? So now we are moving our to 2 dimension. So far we have discussed infinite 1 dimension infinite domain, 1 dimension finite domain, semi infinite domain, and now then we discuss the finite domain case and homogeneous and non-homogeneous. Now let us consider one problem in 2 dimension. So now let us consider the heat equation in 2 dimension. So here we have for simplicity we have taken a very simple domain, that is a rectangular domain. So the boundaries of the rectangle x lying between 0 to a, so it is x equal to 0, it is x equal to a, and here it is y equal to 0 to y equal to b. So this is a rectangular plate we can consider, that we have considered a rectangular plate such that boundaries are kept at 0 temperature. So, it means that the boundaries of the rectangle x lying between 0 to a, y lying between 0 to b are maintained at 0 temperature. Now, if at t equal to 0 the temperature T has the prescribed value some fx y, then we have to show that if you take any point here somewhere here, then the temperature at this point at any given time t is given by 4 by AB summation m equal to 1 to infinity n equal to 1 to infinity f m comma n exponential of minus alpha lambda square m n t sin m pi x by a sin n pi y by b, where this f of mn is given by this expression, that is 0 to a 0 to b f x y sin m pi x by a sin n pi y by b dx dy, and this lambda is given by this, that lambda square mn is given by pi square m square upon a square plus n square upon b square. So, let us see that how we can obtain the solution at any given point at time t greater than 0 here. So, the problem is to solve the following diffusion equation divert t by dt equal to alpha times divert t by divert x square plus divert to t by divert y square, x is lying between 0 to a, y is lying between 0 to b and t is greater than 0, with the boundary condition that at x equal to 0 t 0 y t is equal to 0 and x equal to alpha t alpha y t is given as 0, sorry this is a. So, at x equal to 0 and x equal to a it is given as 0 and y is lying between 0 to b. Similarly, at y equal to 0 and y equal to b, your tx 0 t and tx bt is equal to 0, where x is lying between 0 to a. Now, initial condition is that at t equal to 0 tx y 0 is f of x y and corresponding domain is given. So, let us this solution is given by variable separable form and t x equal to xx yy and beta t. Now, when you take this and look at the equation, that is tt equal to alpha txx plus tyy, when you put it in this variable separable form and divide by x y beta, we have the following equation x double dash upon x plus y double dash upon y equal to 1 upon alpha beta dash upon beta, and call this as minus lambda square. Now, we have two set of equation, one set of equation is this and another set of equation is given by this. So, we have beta dash plus alpha lambda square beta equal to 0, and another we can write x double dash x upon x equal to minus lambda square plus y double dash upon y equal to minus p square. So, we have equation x double dash plus p square x equal to 0 and y double dash upon y square is written as minus lambda square plus p square. Let us for simplicity we write it as minus q square. So, we can write y double dash plus q square y equal to 0. So, your PD, this PD when you take our solution in variable separable form is now reduced to 3 set of ordinary differential equation. One is beta dash plus alpha lambda square beta equal to 0, another one is x double dash plus p square x equal to 0 and y double dash plus q square y equal to 0. And how this lambda is related? Lambda we can write it as p square plus q square. Here we can find out our lambda like this, and solution of this equation is given as a cos px plus b sin px. Solution corresponding to this we can write c cos qy plus d sin qy, and solution of this equation is given as e to power minus alpha lambda square t. Right. Now, we need to find out constant a, b, c, d we need to find out here. So, for that we have to look at the boundary conditions, because so far we have not applied any boundary condition. So, here let us apply boundary condition, that is corresponding to x equal to 0. So, t of 0 by t is given as 0. So, we get a equal to 0 here. In fact, we can do it together or we can do it say simplified, and we can simply say that your x of 0 is equal to 0 equal to x of a. Right. So, this implies that your a is 0 and this implies that your p is in terms of some m pi by L, we can say n pi by a. So, we can simply write, let us do one by one. So, here when you take t 0 y t equal to 0 we get a equal to 0. Then our solution is reduced to t x y t equal to b sin p x c cos qy plus d sin qy e to power minus alpha lambda square t. Similarly, now look at the condition corresponding to y equal to 0, that is t x 0 t equal to 0, and we get c equal to 0. So, this part is also gone. So, now our solution is reduced to t x y t equal to b into d sin p x sin qy into e to power minus alpha lambda square t. Now, let us find out the condition corresponding to x equal to a. Now, when you put x equal to a condition, what you will get? You will get 0 equal to b d sin p a sin qy e to power minus alpha lambda square t. Now, this if we take this as ideally 0 for all y, we will only trivial solution. Similarly, if we take this as say ideally equal, this cannot be non-zero. So, this part cannot be non-zero. So, only condition that sin of p a has to be 0. So, if sin p a has to be 0 means your p a must be equal to some multiple of pi. So, p a is equal to n pi, where n is lying between 1, 2 and so on. So, I can write p as n pi by a, where n is running between 1, 2, 3 and so on. So, using principle of superposition, we get our solution as t x y t equal to n from 1 to infinity a n sin n pi x by a sin q y into e to power minus alpha lambda square t. Now, again we have one more condition at y equal to b. So, t x b t equal to 0, what you will get? We have a 0 equal to summation n equal to 1 to infinity a n sin n pi x by a, and here we have sin q b into e to power minus alpha lambda square t. Now, this is non-zero, this is non-zero. So, this is possible when sin q b is equal to 0. So, it means that sin q b is equal to 0 means your q b is some multiple of pi. So, we can write q as m pi by b, where m is running between 1, 2 and so on. So, using the expression for q, we can write down our solution as a double series as t x y t equal to n equal to 1 to infinity m equal to 1 to infinity a m n sin n pi x by a sin m pi y by b into e to power alpha lambda square t. Now, we already we have p, we have q, then we already have a relation between lambda square as p square plus q square. So, using the value of p and q, we can write the, that pi square m square upon b square plus n square upon a square. So, we have still one AMN is left. So, to identify, to find out the value of AMN, we use the initial condition that at t equal to 0 t x y t is equal to f of x y 0. So, if at t equal to 0, this is f of x y and it is given an n equal to 1 to infinity m equal to 1 to infinity AMN sin n pi by a x sin m pi by b y. So, using orthogonality of sin m pi y by b and sin n pi x by a, you can find out AMN as follows: 2 upon a into 2 upon b equal in 0 to a 0 to b f x y sin n pi x by a sin n pi y y b dx dy. So, our solution is given as t x y t equal to, we are writing the expression for this AMN like this. So, we can write t x y t is equal to 4 upon a b m equal to 1 to infinity n equal to 1 to infinity f m n exponential of minus alpha lambda square m n t sin n pi x by a sin m pi y by b, where f m n we write 0 to a 0 to b f x y sin n pi x by a sin n pi y by b dx dy, where lambda square is given by this lambda square m n equal to pi square m square upon b square plus n square upon a square. So, here we have shown that with the help of variable separable method, we can solve the heat equation in a rectangular domain, and our solution is given by the following representation. So, similarly, we can discuss several kind of domain. Here we have taken only say rectangular domain. We can take a this circular domain, or we can in 3 dimension we can the cylinder we can take, and we can take the sphere. So, all these things can be dealt in a similar way, but due to time consideration constraint, we are not considering all these things, but we say that in a similar way we can handle heat equation in these kind of domain as well. So, with this these remarks we will end our discussion here, and in next lecture we will continue our discussion. So, with this I end. Thank you very much for listening us. Thank you.